today we are looking at very interesting piece of hardware. It is a small DC-DC converter evaluation board by EPC Space, but this is actually a radiation-hardened GaN power converter designed for space applications. This is the EPCSC401, a non-isolated buck converter meant to operate inside spacecraft electronics. Its job is simple but absolutely critical. Take a wide spacecraft bus voltage and generate a stable regulated rail. In this case we're talking about an input between 20 and 50 volts and a regulated 12 volt output capable of delivering up to 5 amps. This is the kind of converter that would live inside satellites, payload instruments, avionics subsystems, or scientific equipment in orbit. The board you see here is actually a characterization motherboard. The small module in the center is the real converter, while the larger PCB exists to let engineers probe signals, connect lab equipment, and perform repeatable measurements without disturbing the electrical behavior of the circuit. We have 4 large banana connectors. These are used for the input supply, the output load, and the ground return. They allow connection to a laboratory power supply and an electronic load while handling significant current. On the left side we also have precise probe points for V in, V out and enable. These are designed for oscilloscope probes, so engineers can observe switching waveforms with minimal measurement error. With the fast GaN switching edges, even a few centimeters of probe ground lead would completely distort the waveform, so this kind of probing interface is essential. Now let's look at the heart of the system, the small module in the center. This is the actual EPCSC401 converter, and internally it implements a buck topology. The converter rapidly switches the input voltage and filters it to produce a clean regulated 12 volt rail. What makes it special is the technology used to achieve that. The controller is the EPCS401, a radiation-tolerant silicon controller originally developed by CERN. This is not a standard commercial PWM chip. It is specifically designed to survive radiation effects such as single event upsets and total ionizing dose. The controller regulates the output voltage, drives the power stage, manages protection features, handles startup and performs thermal shutdown if necessary. The switching power stage is an EPC7011 L7 hermetic gallium nitride device. This is where the most of the efficiency advantage comes from. Gallium nitride allows higher switching frequency, lower losses, and much smaller passive components compared to traditional silicon MOSFETs. In spacecraft this is extremely important because lower losses directly translate into less heat, and less heat means smaller radiators and lower system mass. As said, EPC7011 L7C is a half-bridge gallium nitride power stage. Input logic interface, level shifting, bootstrap charging and gate drive buffer circuits along with gallium nitride output FETs configured as a half-bridge are integrated within a monolithic chip in a custom 7-pin aluminum nitride SMT ceramic package. Looking around the module we can identify the main passive components. The large grey block marked 1R0 is the power inductor. During each switching cycle it stores and releases energy, smoothing the current delivered to the load and controlling ripple and transient response. Around it we see arrays of ceramic capacitors. These serve multiple roles: high frequency input decoupling, containment of switching current loops, and output filtering. In GaN converters, capacitor placement is critical because parasitic inductance must be minimized to maintain efficiency and avoid noise. There is also a very low value current sense resistor that allows the controller to detect overcurrent conditions and protect the system. Thermally, this design follows a very space-specific philosophy. There is no airflow in space, so cooling must happen through conduction. Both the controller and the GaN stage transfer heat through the PCB using heavy copper layers and thermal vias. The bottom heatsink on the demo board replicates the spacecraft structure, allowing heat to be conducted away. Interestingly, the controller's thermal protection indirectly monitors the temperature of the power stage through this coupling. The board also includes system configuration features. The signal threshold is set around 3.2 volts for a nominal 12-volt output, and the converter enables automatically when the input rises above roughly 18 volts. Engineers can also control the enable pin externally and configure how the internal regulator powers the gate drive circuitry. Now let's look at the measurements performed on this demonstration board. The first plot shows efficiency versus output current using a 2.2 microhenry ferromagnetic inductor at a 1 MHz switching frequency. Even at this very high frequency, the GaN power stage maintains excellent performance. At 13 amps load, we measure up to 97.5% efficiency with 24-volt input, and still about 95.4% at 48 volts. This confirms the key advantage of GaN: dramatically reduced switching losses, enabling both high-frequency operation and very high efficiency in a compact converter. Next is line regulation. Sweeping the input voltage from 24 to 48 volts, the output variation stays within about 0.15%. This shows the control loop remains very stable even with the large bus variations typical of 48-volt architectures. Load regulation. From no load up to full load, the output changes less than about 0.45%, demonstrating tight voltage control even during current demand changes. Overall, the EPC401 board combines efficiency, stability, and precision. What makes this interesting is not the topology, but the implementation. In operation, the sequence is straightforward. The bus voltage is applied. Once the threshold is reached, the controller starts switching the GaN stage. Energy flows through the inductor, the capacitors smooth the ripple, and a stable regulated 12-volt rail is produced. It's effectively a reference architecture for next-generation satellite power converters. Compact, efficient, radiation-hardened, and built around wide bandgap technology. For more information, you can visit the EPC Space website, where the EPC401 demonstration board is available with full ordering details and documentation. The controller, the EPCS401, can also be sourced through distribution, including DigiKey and Avnet as mentioned in the material supporting this video. So if you are working on a 48-volt solutions or a high-density DC-DC design for space applications, this is a practical way to evaluate GaN directly on your bench. And if you have questions, feel free to contact us. Thank you.